The next crystal we make is using the body-centered cubic lattice. So, we take the body-centered cubic lattice wherein you have an lattice position at 0, 0, 0 and a lattice position at half, 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 and I put a very simple spherical motif on this lattice. The crystal I obtain is called a body-centered cubic crystal. So, often casually there is a term used in literature, a BCC crystal. So, we have to remember BCC is a lattice, and the crystal, typically when I say a BCC crystal, what they mean is a simple spherical motif which is going on to decorate the BCC lattice. If I have a more complicated motif which goes on to decorate the BCC lattice, then I do not use the phrase BCC crystal in usual sense. So, this is an important point to note, that for instance when I use the word simple cubic, it refers to a lattice, and similarly when I use the word body-centered cubic, it refers to the lattice, and when I monoatomically or for instance use a single sphere to decorate the lattice, I get a body-centered cubic crystal. So, the crystal in the ball and stick view is shown on the right hand side, wherein these spheres are all sitting in the corners of the cube plus the body centering position. Now, there is a space filling model also shown here, which is also showing the same crystal, the BCC crystal, or as I just said, the BCC lattice decorated with a single sphere motif. In some of these figures, we will shade the spherical entities in different colors. It should be obvious that all these entities are identical, and the shading in these contexts have been done merely for better visibility. So, the blue sphere is no different from the red sphere, and the shading has just been done so that you can see the body centering position or the sphere sitting in the body centering position a little more clearly. We will come across later on various other types of crystals wherein the central atom could be different from the atom sitting in the corner. In such cases, of course, we have to be clear that they are actually different atoms. In this case, this is merely for better visibility. So, let me show you a physical model of the BCC crystal. So, this is my ball and stick view of the BCC crystal. So, in this case I have to assume that these spheres are atoms and the unit cell edges are marked in red, and these are additionally just it functions two these other strands perform two functions. One, they hold the central atom in position, but additionally they also show the connectivity. In other words, in a BCC crystal, the atoms are touching along the body diagonal. So, this atom which is located in the center is touching the atom which is located at the corner. On the other hand, the atom sitting in this corner is not touching the other atom which is sitting in the corner. So, we have to remember that. So, the connectivity is between the atom sitting in the corner and the atom sitting in the center, but not along this direction. On the other hand, the unit cell edge is along these directions. So, this is a ball and stick model of the BCC crystal, and we have to notice that this crystal has got the complete symmetry of the lattice. It has got a 4 by m, 3 bar, 2 by m symmetry, which I will write down on the board. And I am using the phrase BCC crystal in the exact sense which I just described to you. And this also happens to be the symmetry of the lattice from which I started off. Let us also look at another view of the BCC crystal, and in this case I will have to look at a space filling model which is on the left hand side of the figure. Okay. So, this is a space filling model, and when we want to understand a crystal, we will have to look at all these alternate views so that I can understand the crystal in totality. So, once again we have to remember, in a BCC crystal, the atoms in the corners do not touch the other atoms in the corners of the vertices of the cube. It is the touching is along the central atom which has been shaded in blue is touching all the other 8 atoms which are sitting on the corners of the unit cell. The next crystal we consider is made out of the face-centered cubic lattice, and as before I mentioned, face-centered cubic, when I say in isolation the word face, the acronym FCC, it refers to a lattice and not to the crystal. And whenever I say use the word FCC crystal, what I typically mean, like in the case of the BCC, is that a single sphere motif has gone on to decorate the FCC lattice, and the crystal I get will be actually something known as the cubic close packed crystal. We will look at this crystal in a lot more detail in coming topics later on, but for now we have to remember that we sometimes call this the FCC crystal, but more technically this is a cubic close packed crystal, and it has been obtained by starting off with an FCC lattice and putting a sphere motif or a single atom motif or a single ion motif on each lattice point. So in this case we have already seen the shortest lattice translation vector is from the 0 0 0 position to the half half 0 position. So I can draw my shortest lattice translation vector between these 2 points, and this is my shortest lattice translation vector. When we were dealing with these lattices, we had made it absolutely clear that every lattice point is identical, and just because the unit cell has been drawn with the origin here, this looks at the center of the face, but I could have as well chosen this as the origin and drawn the lattice, and the lattice would be no different, or the unit cell would be no different. So this is the FCC crystal as we call in normal language, and we have got a space filling model of the FCC crystal. In this case we have to notice that the atoms are touching along this direction, the face diagonal direction, and not along any other direction. So we see this face diagonal direction, similarly there is another face diagonal direction. So let me go and pick up a model to show you this FCC crystal. So I got here with me a unit cell of the FCC crystal, wherein these blue spheres are atoms, these are cells of my edge as marked in red, and these additional strands are the directions of connectivity, which also serve the additional purpose of holding the central sphere in place. So the atoms are touching along this direction, and as we shall see later, this direction according to Miller indices will be labeled as 1 1 0 kind of directions. So we can see that there is considerable amount of space in the center of the body, and these aspects we will consider a little more detail later. So this is my FCC crystal, and we will see there are important directions in this FCC crystal, which is the body diagonal direction, which I have placed upward now, or if I want to show along this direction, the body diagonal direction is an important direction in this FCC crystal, and we will take up this aspect very soon. Now we had used a phrase that this is also called a cubic close packed crystal, and this is because it is made up of close packed planes. The highest density I can obtain in 2 dimensions is by considering an hexagonal layer like this. So this is my hexagonal plane. Of course this plane can be grown to an infinite plane by putting many more spheres. So this is my infinite 2-dimensional close packed structure. So in 2 dimensions this is the close packing I can get, and from here I can go on to make a crystal like that, which is an cubic close packed crystal starting with planes like this, and this operation we will do little later. So in 2 dimensions this is my close packed structure. In 3 dimensions, one of the possible close packed structures is this structure, which is the face centered cubic crystal, which is nothing but an FCC lattice decorated with a single sphere. So let me look at a unit cell of the same FCC crystal, but now in the space filling mode. So this is my space filling model of the FCC crystal, and you can see very clearly that the atoms are touching along these directions, right? And also that the atoms are not touching along the cell edges. So this is my cell edge, and this is my another cell edge. So the atoms are not touching along the cell edge, but they are touching along these directions. Okay. So this is my space filling model of the FCC crystal. We will come back to these kind of space filling models and their importance, especially in understanding various concepts related to the FCC crystal in a later topic. So just to emphasize again, whenever I loosely use the word FCC crystal, I mean a single sphere decoration of the FCC lattice, and when one and only under these circumstances is the structure I obtain will be a close packed structure. I could choose more complicated motifs to decorate the FCC lattice, and in all these cases I would not obtain a close packed structure. We will take up examples of these, but just as a prelude to this thought process, for instance, I can use a fullerene molecule to decorate the FCC lattice to obtain an FCC crystal, or a crystal which has the FCC lattice as its underlying lattice, and such it is obvious that the FCC or the crystal obtained by putting a fullerene molecule in every lattice point is not a close packed crystal. So just because when I use the word FCC, I have to remember it's a lattice, and merely just because a lattice is FCC, the crystal I get from decorating this lattice need not be a closed pack crystal. Okay, so that is point has to be absolutely understood. So let us take up another example which is reinforcing the point I just now mentioned. This is for instance a FCC lattice which has been decorated with a 2-ion motif, a chlorine ion and a sodium ion. This is nothing but the common salt structure, which is the NaCl structure, and the crystal I obtain is the one which is shown in the diagram on the right. So now if you see at this diagram, you see that all the green atoms or the green spheres, or be more precise, in this case the green is the chlorine ion, forms an FCC lattice. Equivalently, all the positions of the sodium ions also form an FCC lattice. This is an important point, and we have already dealt in detail with the concept of a sublattice. So now we can think of two sublattices, in this case two sublattices of FCC type. So I can have one sublattice of FCC type with its origin at this position, another sublattice of the FCC type with its origin at half 0 0, which is nothing but the edge center. The sublattice at the origin is occupied purely by the chlorine ions, which is the larger ion. The sublattice with its origin at half 0 0 is occupied by sodium ions, and the crystal I get can be visualized as an interpenetration of two sublattices of the FCC type. So to go over this concept once again, I have used an FCC lattice, I have used a 2-ion motif. Now the motif would be obviously a combination of a single ion of sodium and a single ion of chlorine. This is my motif, right, and this motif decorates every lattice point, right. So if I have this lattice point being decorated by a sodium and a chlorine, so will this lattice point be decorated by a chlorine and a sodium. And of course it is left as a mental exercise to the reader that actually that if I decorate every lattice point with this kind of a motif, then I would get the crystal as shown in the figure. So this is an exercise which everybody should do. In this case it is perhaps somewhat simple to visualize that how this kind of a motif goes on to decorate this lattice, but in certain other cases it may not be that obvious and a little visualization is required. So please spend some time over this particular structure to understand how it is made up of this lattice and the motif as shown. And as I had mentioned, this crystal I obtain can be thought of as two interpenetrating FCC crystals, or what we may call the FCC subcrystals, which are nothing but a sublattice of FCC decorated by chlorine, another sublattice of FCC type decorated with sodium ions, and I get two interpenetrating FCC crystals or FCC subcrystals, which gives me the sodium chloride structure. Now let me look at a space filling model of the same, which is shown on the left hand side, and you can see that there are these ions of sodium and the ions of chlorine which is occupying this structure. Now energetically, as we will see later, that it is not preferable that my ions of like type, for instance the chlorine ions do not touch other chlorine ions, my sodium atoms do not touch other sodium ions, and this is what is energetically preferable, which is why you see that these ions of the same type, for instance the red spheres, do not touch the other red spheres. So let us look at actual models of these. So this is my ball and stick model of the sodium chloride structure. In this case we should remember that there have been additional red lines here which are wrong. In fact, the unit cell edges are only the corners of the cube, okay. And these are seats, for instance, of the chlorine ion, this is a seat of the sodium ion, and you can see that in the space filling model that this ion, for instance, does not touch this ion, or this ion does not touch this ion. Similarly, the sodium ions are also spaced apart by the presence of these chlorine ions, and they do not touch each other. So this structure looks very nice, and you can see it is a beautiful periodic array, and this was one of the first structures to be analyzed by X-ray diffraction and by Bragg, and so this is one of the beautiful structures. So you should remember here that there is, actually speaking, in a covalent bonding sense, there is no molecule of sodium chloride, that is to be kept in mind. There is no molecule. It is nothing but an array of sodium and chlorine ions occupying space, and we cannot identify a sodium and a chlorine molecule or any such concept which are not applicable to the crystals I am describing here. So, this is my beautiful sodium chloride structure, and so the difference between this kind of a sodium chloride structure which is based on the FCC lattice and a simple sphere decoration of the FCC lattice is obvious. There is no touching of ions, for instance, along the 111 direction. Okay. But still the shortest lattice translation vector is the vector connecting this green sphere to this green sphere, and this is nothing but the half 0 kind of vector. Now, as I mentioned, this structure is not obtained from monoatomic or a monosphere decoration of the FCC lattice, and this is not a closed pack structure. The packing fraction of this kind of a structure is 0.74, or 74% of space is occupied by spheres, and as we shall see, this is only 67%. Okay. So, the packing fraction of this kind of a structure is lower, and therefore, I cannot call it a closed pack crystal merely because it is based on the FCC lattice. So, this has a lower packing fraction which is 0.67. So, as I pointed out, we can start with an FCC lattice and decorate it with more and more complicated motifs. Some more examples we will consider later in the course. In the previous example, wherein we started with the FCC lattice, we had used two different kind of ions to decorate the lattice. In this case, we consider what is known as the diamond cubic crystal. Okay. In the diamond cubic crystal, we have atoms of the same type, which is nothing but 2 carbon atoms, and as you might be knowing that the carbon atoms in diamond are sp3 hybridized. That means the bond angle between central carbon and all are tetrahedral. So, they are tetrahedrally bonded to the single carbon atom, and this tetrahedral bond pervades in 3 dimensions to complete the kind of structure I am showing. So, let us start with this FCC lattice as before. Let me put the 2 atom motif, and in this case the 2 atoms of carbon are located at 0, 0, 0 and half, quarter, quarter, quarter. So, if I do that, I obtain a crystal which is shown here. So, I have an atom at 0, 0, 0, another atom of at quarter, quarter, quarter. So, I take this 2 atom motif and I put at every lattice point of the FCC lattice, at this lattice point, so forth, and I will get this crystal. In the figure shown, which is the ball and stick kind of a model, we have to remember that atoms have been colored differently for better visibility, and all atoms are nothing but carbon. So, this is carbon atoms, and just for better visibility we have shaded them differently. These central carbon atoms located within the unit cell form a tetrahedron as drawn by this outline. So, this is just to make the visibility better, that these actually form a tetrahedron, and an important point which is to be noted in this crystal is that it has no normal 4-fold rotational symmetry. So, this is an important point to note, that the diamond cubic crystal has no rotational, pure rotational 4-fold symmetry. And the symmetry of the crystal has been lowered below that of the lattice. So, this is not the symmetry of the crystal anymore. As I am talking about this diamond cubic, often you will find an acronym for diamond cubic as DCC. I will utilize this option to actually write down all the common acronyms which we use. For instance, we use the acronym SC, FCC, BCC, DC, and one more acronym we will come across later is HCP. Please remember, they look very common in terms of their description, but we have to remember these 3 are lattices and these 2 are crystals. Okay. We have already constructed crystals made out of these lattices, and additionally just now we are considering a crystal made out of this FCC lattice, but is called the diamond cubic crystal. And we have seen that this diamond cubic crystal does not have a 4-fold rotation axis, a pure 4-fold rotation axis. We will analyze the symmetry of this crystal in a little more detail later on, but for now it is important to note that the symmetry of the crystal has been lowered with respect to that of the lattice by the presence of additional atoms in the motif. Okay. Now this kind of a model which is shown on the left is an important kind of a model which you would often see in textbooks, wherein this tetrahedral order I was talking about, wherein the central atom is touching this atom and is touching this atom, then it goes, this tetrahedral order pervades in 3-dimensional space to occupy the entire space. Now again we note that this crystal we obtained is not a close packed crystal. Another example to emphasize this fact, that just because some crystal is based on the FCC lattice, it need not be a close packed crystal. Maybe we will perform this exercise later, or is left as an exercise to the reader to actually calculate the packing fraction for this crystal. Now this crystal is completely covalent and is very different from the kind of bonding we considered in the sodium chloride crystal. So these bonding differences also we will consider very soon, and we will try to analyze crystals on what kind of rules would govern what kind of a crystal would form. But we have to remember that this diamond cubic crystal is covalently bonded, but nevertheless we cannot call any small part of this crystal as a normal covalent molecule, but this entire order pervades to the entire crystal, and therefore this is a completely sp3 hybridized atom of carbon which is giving rise to this crystal structure. This kind of a crystal, as you know, the diamond cubic crystal has very interesting properties. For instance, it is one of the hardest materials and it has a very high refractive index. It has a very poor thermal conductivity, or to be precise, it got very poor electrical conductivity but has got very good thermal conductivity. So this is a very strange kind of a combination of properties. Typically when you are talking about electrical and thermal conduction, it is usually the electrons which are responsible for both, and therefore electrical conductivity and thermal conductivity go hand in hand. In this crystal we find that it has got good thermal conductivity but very poor electrical conductivity. So it is an insulator. So to summarize, the second kind of crystal we have made out of this FCC lattice, or the third kind, we have started with the FCC lattice. We have put a 2-carbon motif to make a crystal which is the diamond cubic crystal, and this diamond cubic crystal is still called a cubic crystal because the 3-fold axis has been preserved. So let us look at a physical model of the diamond cubic crystal and understand the presence of this 3-fold. So this example is an ample proof that if 4-fold is lost, still you can call a crystal as a cubic crystal. But if the 3-fold is lost, then you will not, or more precisely, if there are no 2 3-folds, then such a crystal cannot be called a cubic crystal. So this is my unit cell of the diamond cubic crystal, and you can see that the tetrahedral arrangement has been shown by these red lines, and these white lines, unfortunately there are 2 white lines, you will have to focus on the ones which are on the cell edges are the ones which are the unit cell edges. Okay. So you have the tetrahedral order progressing from the central atom to the various atoms. If you look at along the body diagonal, you will see that it has got 3-fold rotational symmetry. So I will use the other camera angle to actually show this 3-fold rotational symmetry. So now I am looking at my diamond cubic structure along the body diagonal which has been positioned from the top. So now this is my 3-fold direction. So my 3-fold direction passes along the body diagonal. Okay. The inner or the carbon atoms located within the unit cell themselves form a tetrahedron, and this is along the 3-fold of that tetrahedron as well. So when I am saying 3-fold axis, what I mean, if I may rotate it by 120 degrees, I will end up with the same structure. So again I can rotate by 120 degrees and land up with the same structure. I can do this operation infinite number of times. So this body diagonal of mine is a 3-fold, and any body diagonal of this cube, for instance, if I take this body diagonal, again would be a seat of the 3-fold axis, and it would have all the 4 directions, this body diagonal, all the 4 of them as 3-fold axes. Okay. And therefore in effect it will have 4 3-fold axes, which is what is a defining characteristic of cubic crystals, and this crystal I have generated would be called a diamond cubic crystal. So we have pointed out that this axis which is along the cell edge is not a direction of the 4-fold, but we will see it is related to the 4-fold but in a different way. So to summarize this slide about diamond cubic crystals. DC, when I say, it refers to a crystal. It is a 2 carbon atom motif. It is different in bonding characteristics from the sodium chloride crystal, which is got ionic bonding, while this is a covalent bonded crystal. This is not a close packed crystal, and more importantly I should note that when I talked about the BCC crystal, for instance this was my BCC crystal, this is also not a close packed crystal, but it still had a close packed direction, and the direction was the direction of the body diagonal. So, we had the case, for instance, the face-centered cubic crystal, which was itself a close packed crystal. It had close packed directions which was along the direction I have shown here. This is the close packed direction, the face diagonal. So, it is a close packed crystal with close packed directions in it. When we went to the BCC, we saw that it is not a close packed crystal, but it still has close packed directions which is along the body diagonal of the body centered cubic crystal. Now, we have it with us another example, which is the diamond cubic crystal, which neither is close packed nor has it any close packed directions, because if I try to travel along the direction of touching, which is the body diagonal direction, I see that this atom is touching this atom, but then the next connectivity is from this quarter position to a half 0 kind of position. So, that continuous path of carbon atoms along the body diagonal is missing, and therefore, this kind of a crystal is neither close packed nor has close packed directions. Now, another aspect we could have considered was close packed presence of close packed planes. So, for instance, when I am talking about a FCC crystal, this is a close packed crystal, it has got close packed planes, and these close packed planes are we will consider this in a little more detail later, for just for peeking ahead a little bit now, are these kind of planes which are drawn by this kind of a plane. So, we will see the Miller indices of this plane later will be the 1 1 1 kind of plane, and this kind of a crystal is a close packed crystal. It has got close packed planes, but also has got close packed, when in addition has got close packed directions. This crystal, the body centered cubic crystal, is not close packed, it has no close packed planes, but has got a close packed direction. This diamond cubic crystal itself is not close packed, it has no close packed planes, in addition it has got no close packed directions. So, we have to remember all these subtle points, that when I am describing a crystal, we should not only try to identify the structure, how is it close packed or not close packed, but additionally look out for these special directions which are the close packed directions. Now, we have already seen that the symmetry of the crystal can be lowered if you put a motif which is in a certain way. Now, we will consider some of the examples in 3 dimensions. Some of the 2-dimensional analogues of this we have already seen. What happens when I try to put motifs which do not have much of symmetry? For instance, on the left hand side of this figure is shown a figure wherein I have put a very irregular looking kind of a motif. Typically, of course, in nature you will not obtain a motif which looks like this, but typically it could be a combination of many atoms. You for instance could be having a molecule, a polymeric molecule, or any other kind of large molecule with many atoms which has no symmetry in itself. Okay. When I put such a motif on this cubic lattice which I started off with, you can clearly see that all symmetry has been lost except translation, and therefore, the crystal on the left hand side, even though it is made up of the simple cubic lattice, is a triclinic crystal and not a cubic crystal. The lattice parameters are not affected by this process, because the lattice parameter I assume is the original ideal geometrical lattice parameters, which are A equal to B equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. Now, the figure on the right hand side I have made by decorating my simple cubic lattice with an shape of an arrow, but now I have not put this arrow in a single orientation. So, in other words, going from one point to the other, I just rotated my arrow any way I like. So, when I go across this 3-dimensional space infinitely in x, y and z direction, I am going to be putting these arrows in various orientations. Now, we have to remember what I obtained by doing this process, like we saw in the case of the 2-dimensional version of this. The final product I obtained is actually not a crystal, it is amorphous. And this blue outlines originally which formed a unit cell of the lattice is no longer a unit cell of the crystal because I am not obtaining a crystal by this process. We shall see that how can we, like I pointed out in the case of the two-dimensional version of this, that how we can deal with these kind of crystals or these kind of amorphous structures within a framework of crystallography. We will consider this a little later. So, we have to remember that just because we start with a cubic lattice, I do not have to land up either with a crystal with the highest symmetry, which is 4 by m 3 bar 2 by m symmetry, or in extreme cases I can even land up with triclinic or amorphous materials, even starting with the cubic lattice. I could of course started with a body-centered cubic lattice or a face-centered cubic lattice, but for simplicity I chose the simple cubic lattice. Now, this is perhaps some of the important slides we are going to consider next, and the importance of these slides is because so far what we have been doing is what is called mathematical crystallography, and of course we extended the mathematical crystallography a little bit by putting these kind of atomic motifs like the carbon motif, 2-atom carbon motif for the sodium and chlorine ions, or for instance in the FCC case we could have chosen a carbon, copper or zinc or any of these atomic species. For the FCC case I would choose copper or nickel, and as you know, when it forms a metallic bond, then you will have copper or nickel ions which will decorate the FCC lattice to give you a copper crystal or a nickel crystal. So, there has to be absolute distinction between the ideal mathematical crystals and real crystals, and some of these examples we have considered should not mislead you into thinking that in nature there is no connection between the symmetry and the geometry. So, the coming slide will explain to you that actually in real practical examples, especially in atomic examples, we could have a connection between the geometry and the symmetry. In other words, when I put a lower symmetry motif onto a higher symmetry lattice, it could so happen that the lattice itself will undergo a distortion, okay, because of the atomic entities would repel or attract each other, the usual bondings, and it can lead to a different kind of a crystal which would be consistent. That means the lattice would become or the geometrical aspects would become consistent with the symmetry aspects. Okay. So, to state the important point, from reading some of the topics so far, one might get an impression that the geometry of the unit cell has no connection with the symmetry. It can happen in ideal mathematical crystals or crystals which we make. Some of the natural crystals, there will be a connection more often than not. One may even be tempted to conclude that the choice of, for instance, the square prism unit cell, the tetragonal unit cell for the tetragonal crystal is purely coincidental. Such a choice you might think is purely coincidental. Let me consider one example at this point of time to clarify the matter. So, Mr. Patel has a question.
I have one question that was related to just before slides. For maximum close packing, there is a close packing fraction is 74%. If we choose same one type of motif, and for NaCl we take here two types of motif, and here close packing is reduced. So how we can define any crystal is close packed or not? You just taken some planes or direction in the close packing. So I want to clarify. Just we can.
Okay. Very important question now. Mr. Patel's question is that I started with a single sphere motif and obtained a close pack structure which had a packing fraction of 74%. Now, how do I conclude that a given crystal is close packed or not? The first thing we saw the requirement was the existence of spherical atoms. Now, we could have atoms whose electron densities on the outer level could be very different from spheres, and they may not behave like an ideal close packed spheres, and therefore the packing fraction may come down from ideality. Later, when we consider hexagonal close packed crystals, we will see that this could be an important issue, because more often than not, an ideal close packing in the hexagonal format would give you an ideal C by ratio. But we will see that most real crystals deviate from this ideal C by ratio, which means they deviate also from the ideal packing fraction which we assume. Now, what is the criteria that we understand that it has to be close packed or not? It is the packing fraction. Suppose I calculate my packing fraction, it is less than 74%, which is the theoretical maximum, then I would conclude that it is not a close packed crystal. I will not base my conclusions either on the presence of close packed directions or the presence of close packed planes. It will purely based on the volume close packing, which means the packing fraction of space. So, this is a very important question to be kept in mind, and perhaps when we take up hexagonal closed packed and other crystals, this may become more obvious. So, coming back to the connection between geometry and symmetry, in real crystals with atomic entities, nature decides the final outcome and we are left to analyze the outcome in the language of crystallography. So, there are crystals of, we will see some examples which we make ourselves. We could make crystals, for instance, out of this big entity out in my hand. So, more examples we will see soon, but there are crystals which are, at least even though we make them artificially in the laboratory or may occur naturally in, but they may be assembled by themselves. Okay. But in any case, if nature or an artificially synthesized crystal is made, then it is our job to analyze the outcome in terms of the language of crystallography. So, it is not that in every case we can make a crystal starting with any kind of motif or any kind of entity. Sometimes nature decides what will be the outcome. So, let me consider this one example to connect my geometry with symmetry. So, for instance, now I take a unit cell of a cubic lattice and now I assume that these are two atomic entities, real atomic entities for now. If I now decorate this lattice with this atomic entity, which is now my motif, I will get a structure like this. Now, there is no reason to assume that the way I am drawing it, that this should not sit in the center. So, an alternate way of drawing the same thing is that there is a orange sphere and a gray sphere and they will sit like this in the unit cell. Now, let me use two views to understand this kind of a crystal. I will use a front view and I will use a side view. So, I start with a simple cubic lattice, I put a 2 atom motif and the structure I obtained like this, which I shall understand with two views. Now, what would happen to this arrangement? Typically, you would see that because there is an additional entity here, this direction would be, for instance, this direction would have a longer length as compared to this direction where my atoms, this atom can actually touch this atom. So, if I look at, for instance, the front view, I would see a configuration like this. So, there will be an atom here, there will be a gray and there will be another orange. So, I will see that this shape will turn into a rectangle, while this atom is touching each other. So, this is the shorter length. If I look from the other direction, which is the side view, I will see that actually I can see a 4-fold axis and the 4 atoms would be touching each other, right. So, what is the resultant? The resultant would be a new kind of a unit cell, which I have shown the center here, right. Therefore, the conclusion from this exercise is that when I put motifs of lower symmetry, then the typical unit cell will also lower down to that kind of a, to adjust that kind of a motif, and therefore, there will be no conflict between the symmetry and the geometry. So, now this is a unit cell of the tetragonal crystal. The crystal itself has got tetragonal symmetry, that means it has got only one 4-fold axis. The 3 axes remain orthogonal, that means alpha is equal to beta is equal to gamma is equal to 90 degrees. So, this is perhaps a simplistic example, but nevertheless brings out the important point that the kind of motif we have put automatically leads to a unit cell in which A is equal to B, but not equal to C, and the unit cell will be a square prism, that of the tetragonal crystal system, and hence the lower symmetry of the motif can lead to an altered geometry of the unit cell of lower symmetry. In other words, the common shape of unit cell you would see in textbooks. In other words, many textbooks will mention that tetragonal crystal would mean A is equal to B is not equal to C, alpha, beta, gamma is equal to 90 degrees, and there is usually no mention of the symmetry aspect. But you can see from this example that the symmetry and the geometry sort of coincide with each other and the language become consistent, at least in these kind of atomic entities. After making crystals in 1, 2 and 3 dimensions, let us now return to our main flow, which is considering the various crystal systems. This may be a good point to revise some of the aspects, perhaps not in detail, but a little revision. So, we have seen that lattices can be constructed using translation alone. The definition of crystals is based on symmetry and not the geometry of unit cell, and we have seen that often these two coincide, or they can coincide at least in the case of some real crystals. Crystals based on a particular lattice can have symmetry equal to that of the lattice or lower than that of the lattice. Based on symmetry, crystals are classified into 7 types known as the 7 crystal systems. We will take up these 7 crystal systems one by one very soon. we can put all possible crystals into 7 boxes, which we call the 7 crystal systems. In advanced kind of a consideration at this point of time, but it might sort of enthuse you to go ahead and read about these kind of aspects in a more detailed text like from elementary crystallography by Berger. And the points I mention are: symmetry operators acting at a point can combine in 32 distinct ways to give the 32 point groups. Lattices have 7 distinct point group symmetries which correspond to the 7 crystal systems. So, there is a very sound basis of why we should have 7 crystal systems, right, that is absolutely clear. So, the important points to highlight are the point which has been outlined in this dotted box. Now, we are asked this obvious question that since we are now talking about crystals, the definition of crystals based on symmetry. So, we have to ask what are the symmetries of the 7 crystal systems. In other words, what is the characteristic symmetry of all the 7 crystal systems. For instance, we have already seen that cubic crystals need to have 2 3-fold axes. So, the cubic crystal needs to have 4 3-fold axes which can give you can start with 2 and the remaining 2 would be generated automatically. Hexagonal crystal has 1 and only 1 6-fold rotation axis. And it is an important point to note, since we are now talking about crystals, it is not necessary that this 6-fold need to be a regular 6-fold. It could be an alternate form, like for instance, it could be a rotor inversion axis or a screw axis as well. So, other kinds of symmetry operators which have 6 in them need to be present, at least one of them need to be present. The tetragonal crystal, for instance, has only one 4-fold axis. If there are 2 4-fold axes, then obviously it goes into the cubic class. This 4-fold again, like the 6-fold, need not be a pure normal rotation axis, but could be actually a roto inversion axis. The trigonal crystal has only one 3-fold rotation axis, and of course, as before, it could be a roto inversion axis. So, if it had 2 3-fold axis, it will come under the cubic class. It has only one 3-fold axis, it will come under the trigonal class. And we have seen an alternate name for this trigonal, it is also called the rhombohedral crystals. But I prefer the term trigonal because the word tri refers to the 3-foldedness, which is the symmetry of the crystals coming under this class. Now, we also did this operation wherein we started with the cube and pulled it along the body diagonal, which the operation was such that it retained this one 3-fold axis and destroyed the other 3-fold axis. So, we saw that how we can start from a cubic kind of an unit cell and go to the trigonal kind of an unit cell, which is otherwise called the rhombohedral unit cell. The orthorhombic crystals have 3 2-fold rotation axes perpendicular to each other. This could of course also be roto inversion axis, and we will actually list down the point groups which would go in this orthorhombic class of crystals. The monoclinic crystal, on the other hand, only one 2-fold axis, which could also be a roto inversion axis. The triclinic crystal has no kind of symmetry except translational symmetry. However, we can write it as a 1-fold symmetry or a 1-bar symmetry. In other words, you can still call it a crystal having a 1-bar symmetry and come under the triclinic class. So, even though we say there is no symmetry, we actually mean that it has got translational symmetry, and in addition it could have an 1-bar symmetry. So, this point has to be kept in mind regarding triclinic crystals. So, of course, 1-fold symmetry itself is a trivial thing to describe, but 1 bar is slightly not so trivial, and similarly translation is definitely left in the triclinic crystals. We have listed in this table, for instance, the very essence of the symmetry which needs to be present in these various classes. More symmetries could be present, part of the point group, and we will list them one by one when we soon consider the 7 crystal systems. So, we have the 7 crystal systems 1, 2, 3, 4, 5, 6, 7, and these are the characteristic symmetry of these crystal systems, and the complete elaborate point group symmetries will be written in the coming slides. So, let us now consider the 7 crystal systems one by one. When we consider these crystal systems, I will use the following template. I will use the name of the crystal system, I will use the typical choice of the unit cell and the lattice parameters describing that unit cell. I will also show a diagram of the preferred unit cell. I will also list under the crystal system the possible Bravais lattice from which they have been constructed. I will put down the point groups belonging to this crystal system, and in at least the cubic case I will show you additionally the shape of these crystals, which is a very important concept. So, this is my template for describing the 7 crystal systems. So, let me start with the simplest or the high symmetry one, which is the cubic crystal. We know these interrelationship between the lattice parameters from before, and this is how my unit cell of a cubic crystal typical choice would look like. You already seen from previous examples that these are the possible Bravais lattices from which you can construct a cubic crystal. And now there is something slightly more sophisticated, which is the listing of the point groups. Though from an elementary course point of view, it may not be necessary to remember each one of these point groups, but some of the essence need to be noted. For instance, I mentioned that a cubic crystal needs to have this 2 3-fold axes, which would of course result in 4 3-fold axes. So, if at all I am writing down a point group of a cubic crystal, you will see that the 3 appears in the second place. See, in every one of these point groups there is a 3 in the second place. Of course, it need not be a normal 3, it could be a 3 bar, which we have also pointed out in the slide which we had considered here, that it need not be a pure rotation axis, it could be a, for instance, a roto inversion axis. Okay. Now, this is listing also brings to you the other important point, that when I had a cubic lattice, it had this highest symmetry, which I call the holohedral symmetry of these crystals. So, the cubic lattice and some of the cubic crystals which I can construct can have this highest symmetry, which is the one written on the right hand side, but it could also have some of the lower symmetry ones. For instance, this 2 3 is a possible symmetry of cubic crystals. And when we had mentioned the concept of space filling, we had considered that though on one hand there is a concept of space filling and there is a close association of the concept of space filling with crystals via the concept of the unit cell, but we should never confuse the concept of space filling with the presence of symmetries. And this is a very good example to show this, the 2 3 symmetry. For instance, tetrahedra do not fill space, but 2 3 symmetry, which is tetrahedral symmetry, is allowed in crystals, and more precisely it is allowed in classified under the cubic crystals. So, this has to be absolutely clear at this point of time. Another point worthwhile to note is that, for instance, 4 by m, 3 bar, 2 by m kind of a crystal would have a center of inversion, while a crystal having a 2 3 symmetry will not have a center of inversion. In other words, if I am looking at a property which has a symmetry exactly equal to that of the point group of the crystal, okay, in that case if you invert the direction, the properties need not invert, just because for instance in such a crystal with 2 3 point group, the 1 0 0 direction will, or the positive x direction will not be equal to the negative x direction. So, that has to be remembered because the crystal does not have a center of inversion. So, it is very important for me to understand not only that what lattice a crystal starts off with, but what is the exact point group symmetry of the crystal in order for me to correlate it with the properties. One of the important properties I may look out for is the shape of the crystal. So, for instance, I am now considering what is known as the well grown crystal, which is otherwise known as the eumorphic crystal. So, when I grow a crystal, and of course, I will assume that the energetics determine the shape of the crystal, that means the outer shapes is well formed, then cubic crystals will typically grow in various shapes. I mean grow, or more importantly let me consider an equilibrium shape for now. That means that the outer shape is an equilibrium shape of the crystal, but more importantly what I need to note that the equilibrium shape of the crystal, for instance for the cubic crystals, could be a cube or an octahedron, or for instance this is a truncated octahedron which is known as the tetrachedecahedron, and we have seen previously that this tetrachedecahedron is a space filling solid. Okay. Now, it could grow in one of these 3 shapes or many other shapes which are between all these shapes. Okay. So, this is, let me repeat this important point. For a crystal, if it has been well formed and it is the equilibrium shape, that means the global energy minima shape I am considering, a finite crystal, then the outer shape of the crystal for a cubic class would, say for instance, now I am considering the highest symmetry ones, for instance the 4 by m 3 bar 2 by m symmetry ones could be not just a cube. The crystal could have a shape which is an shape of an octahedron as well. It could also have a shape of the tetrachedecahedron, and herein is an important point to note that the external shape reflects the inner symmetry present in a crystal. So far we were dealing with the mathematical crystallography, right, the language of crystallography in a pure mathematical sense, but now we are talking about a very practical aspect, properties of crystals, and we will mention something more about properties of crystals very soon. And when we talk about properties of a crystal, we have to remember, for instance, this is one property, the shape of a crystal that reflects the inner symmetry of the crystal. Of course, the crystal has to be well formed, and sometimes it is very difficult to get these well formed crystals. So, and it mean, for instance, even the higher symmetry cubic crystal need not just be a form of a cube. The external shape could be in the shape of an octahedron as well. So, that has to be remembered, and this is where there is a confluence of the concept of mathematical crystals and real crystals. Even though we have spoken a language of point groups, symmetries, etc., but now we have a physical crystal which in some way is, that is where the joining of both the concepts, the mathematical and the physical world takes place, and this is one of the properties. The joining would also take place in many other ways, in many other properties, but this is a beautiful example. And before even, for instance, the formal mathematical language of crystallography developed, people have been observing that crystals actually grow in shape, and this has been some of the reason of quite a bit of interest of mineralogists in crystals, is the beautiful shapes they would grow under and some of the beautiful optical properties these shapes would lead to. And so we can see that these crystals can grow in these shapes. A lower symmetry tetrahedral crystal, for instance, could grow in the shape of a tetrahedron. There are many more shapes they can grow in, but the essence for you to remember for now is that the external shape reflects the inner symmetry. That is an important point to be noted down. So, let me write this down on the board. External shape of eumorphic crystals So the external shape of, for now I consider an equilibrium crystal of a well grown or eumorphic crystal reflects the inner point group symmetry of the crystal. So once again to warn you, just because I am using the word cubic crystal, it does not mean the shape of the crystal has to be cubic. It could be one of the other shapes which has the same symmetry. In this case, just as a warning to our advanced readers, that we do not consider space group symmetries, because space groups additionally have translations. So at the scale we are talking is a macroscopic scale and not the micro scale, and these translations are at the micro scale and they are not typically considered in these macro shapes. So the translations of the order of atomic translation vectors or lattice translation vectors, while this shape is the macro scale, which could be a crystal typically could be grown as big as my hand or typically of centimeters, and therefore this is the macro scale, and therefore I can ignore the space group symmetries which have translations in them, and all I need to consider at this stage is the point group symmetry. So this is what I wrote down on the board. So just to emphasize this point again, the statement is right here for you. Now we will see some more points regarding properties of crystals, and we will state an important principle very soon. So let me summarize the important points regarding some of the aspects of cubic crystals we have considered. We have seen that cubic crystals can have a shape of a cube or octahedron, truncated octahedron, or many other possible shapes. We have to note that some of these polyhedra have same rotational symmetry axis, noting that cube and octahedron are regular solids, platonic, while truncated octahedron with two kinds of faces is not a regular polyhedron. we have seen that the external shape is a reflection of the inner symmetry at the atomic level. If you find it uncomfortable to work with point groups, please ignore them at this stage, but remember that point group symmetry is nothing but a combination of some of the symmetry elements. Cubic crystals can be based on the simple cubic, body centered cubic or the face centered cubic lattices by putting motifs on these lattices. After the crystal is constructed based on these lattices, it should still have a three-fold symmetry if it has to come under the cubic class, which usually crystals made of single atomic entities have. If we have also seen that if a crystal does not have this feature, it is not logical to classify it under the cubic class. So, I have certain models of cubes here which have been cut along various directions, and these models for now I will use to demonstrate the fact that how what you might call the shape of a crystal or the faces which are developed in the crystal. If a crystal has only these kind of faces, for instance this is now a simple cubic crystal, then it could have only these kind of faces, in which case it will have a shape of a cube. But it could have a combination of these kind of faces and these faces which is now being truncated along the 1 1 1 direction. So, you can see that if I look at this face, it has got a certain atomic density. On the other hand, this face like this has a lower atomic density in the case of the simple cubic crystal. A crystal, for instance, this is another alternate model of the same simple cubic crystal, could show faces which are of this type. The face you can see clearly that has been cut along, and you can see that these faces could also be developed, and these faces also, as you can see, have a lower atomic density than the faces of this type wherein all 4 atoms are touching each other, while in this direction when we cut a plane like this, you can see that atoms are touching along this direction, but not along this direction. So, of course, just the atomic density will not determine the equilibrium shape of a crystal. The equilibrium shape of a crystal typically is constructed by a method known as the Wolff construction, but therein we consider the energetics, that means what is the energy of all these faces, and if the lowest energy happens to be for this kind of a cubic face, then it will have a cubic shape. If it happens to be for the lowest energy singly for instance for this kind of a face, the crystal could show an octahedral kind of a shape, or there could be a more complicated shape in which you could have these kind of faces, which is also this kind of a face, this kind of a face and this kind of face. So, there could be a combination of various kind of faces which could develop, and that would determine the form or the external shape of the crystal.